paper says quiz 7. This is not a quiz. This is something that I used to do in my younger, meaner days. The course policy used to have quizzes every week. And so the students complained bitterly. And so in my old age, I kind of got soft, and I don't do this anymore. But it's still, so cross that out. It's not a quiz. This is today's lesson. Okay? And what we're going to do is we're going to take a look again at the phase plot. And one of the things that I mentioned in a previous meeting was that, at least for this course, anything that I ask you to do by hand, for the most part, I'm going to have positive signs here, because the rules for sketching things quickly are going to have positive signs. The lone exception, the one exception, might be if there's a minus sign up here. And so the takeaway today is I want to take a look at these 4 different transfer functions. And basically, the only difference is you'll see that there are minus signs scattered around at different places. And the takeaways I want you to remember is that the phase plot is sensitive to these minus signs. The magnitude plot is not. Magnitude, remember, we take the square root of the sum of the squares when we do complex numbers. Take the real part and the imaginary part. You've got to square each of them and add them and take the square root. The squaring process makes the minus signs irrelevant. So the magnitude plot for this and the magnitude plot for this and this and this will all be identical. So even though the systems are radically different, their frequency response from a magnitude standpoint looks identical. But the phase plot is where all the information is with the minus signs. So here's the object. The quiz at the time was you're given a bunch of frequency responses. They're plotted at the bottom. If you just come in, pick up a sheet there, pick up a worksheet if you're just coming in. And what we want to do is we want to basically match A, B, C, or D to each of these. Okay? And so I think it'll be a quick meeting today. All right, so these are the 4 different transfer functions. They have a minus sign appearing at different places. And we've got different phase plots right here. Okay? 4 different phase plots associated with 4 different transfer functions, 4 different models. All right, so let's do the easy parts first. This is phase. Typically, the units here are going to be in degrees. And this is the frequency, and we need to have units in class, in school. S is equal to j omega, so remember S is equal to j omega. This is frequency response, and I think my pen's about to run out here. Maybe not. Okay, radians per second. Label that as radians per second, radians per minute, radians per fortnight, some unit of time. Okay, now we want to take a look and see what the phase characteristics here. This is the classical problem that we should know how to handle. We know that in the magnitude plot, the corner is at omega equal to 1 in the magnitude plot. So in the phase plot, there should be corners at 0.1, a decade below, and 10, a decade above. Okay. So, and this being a simple case, okay, S is equal to j omega, so we're looking at the function j omega plus 1. So when omega is very small, the number is just 1, so the phase is 0 degrees. So it's got to be either this case or this case. When omega is small, the phase is 0 degrees, so it's got to be either B or C. Okay. The corner frequencies are here and here. Okay, here's the corners, 0.1 and 10. Those are the 2 corner frequencies. Now, when omega is large, this thing looks like 1 over j. 1 over j has a phase of negative 90 degrees. So when the frequency is large, we go to a phase of negative 90 degrees. So it must be this curve. Now, the straight line approximation looks something like this. So you were sketching it by hand, you would draw these straight lines. It starts off flat, hits a corner, it changes to minus 45 degrees per decade. After 2 decades, it's gone down 90 degrees, and then it goes out flat again. The relative degree of this problem, the number of poles minus the number of zeros, the relative degree is equal to 1, and so it ends up at negative 90 degrees. So we end up at minus 90 degrees. So the answer is, the one that matches this should be graph C. Any questions? All right, let's take a look at the next one. What would match, which graph matches this plot G2? The only difference is we now have a minus sign in the numerator, in the constant term. And so whereas up here, this gain is equivalent to 1 at an angle of 0 degrees. Now here, this term looks like 1 at an angle of plus or minus 180 degrees. So we just need to take the identical graph to C and shift it by 180 degrees. Everything else about the functions are the same. The denominators are the same. So we need to take a look at which one of these looks like just C, but shifted by 180 degrees. Okay? So the logical answer is A. Those are the 2 easy cases. These are the cases that I'm going to hold you accountable for in this class. We should be able to sketch the frequency response, the phase response of a case where the function has no minus signs, and where the minus sign is just something that can be factored out easily out in front like this. Okay, life gets a little bit more complicated here. The rules that I talked about before for sketching kind of go out the window. The general shape, where the corners are, that doesn't change. But the actual phases do change a lot. Okay, so remember, what is frequency response? Frequency response means S is equal to J omega. So we should have, this is going to be now J omega minus 1. So when omega is very small, we have the number minus 1. So that's a phase of 180 degrees. Or it could be a phase of minus 180 degrees. So it's either this one, a phase of 180 degrees, or it's a phase of this one, minus 180. So the answer is it's either going to be A or it's going to be D. One of these two might be a candidate solution for this function. Now, which one will it be? Well, what we could do is you could stick a number in here, try some other omega. You could maybe try J equal to 1 or something else. Or we could take a look at when omega is very, very, very large. When omega is very, very large, this thing looks like 1 over, it overwhelms this. Okay, so the phase is minus 90 degrees. So I'm going to guess that it's this one. When omega is large, it goes here. We might try an intermediate number in here. Try some frequency point here, like omega equal to 1. Let's stick omega equal to 1. Try a couple points. That's what we do. All right. Let's stick in omega equal to 1. Then you get 1 over J minus 1. And take a look at the phase of that. Okay. So you look at the phase of this number, but it's on the bottom. So it's negative 1 plus J. Negative 1 plus J. Negative 1 plus J has a phase of 135 degrees, but it's on the bottom, so it's negative 135 degrees. So it's right here. So when I try omega equal to 1, it matches that number. So the one that matches here is D. Now we could use the process of elimination, and since he said we only have 4 answers. The logical choice must be B here. But we could go through the same process again. This is 1 at an angle of 180 degrees. And on the bottom here, we have j omega minus 1. And so when omega is very small, we have negative 1 over negative 1. Negative 1 over negative 1 is just 1. And so again, we're starting off at 0. So it's either this plot or it's this plot. Now, when omega is huge, it overwhelms the bottom here, then you get 1 over j omega, which is negative 90 degrees, but you got 180 degrees up here. So negative 90 plus 180 gives you 90 degrees, so we end up over here. Try an intermediate number, again, if you wish. When we try an intermediate number here, remember we've got 135 degrees, we're down here. Now we're just shifting it about 180 degrees. We were down here on this one, shift about 180 degrees, that brings it up to here. So the answer is this one's B. Okay. Okay, so the takeaway today is the following. With phase plots, be careful when minus signs appear. Be careful when the minus sign appears. But the only easy case is the second case. Alrighty, any questions? Very good. Okay, so now we know how to sketch the Bode diagrams for both the magnitude and for the phase. What we're going to do on Wednesdays, we're going to take Bode diagrams again are on semi-log plots. On Wednesday, we're going to take a look at a different plot. It's the same information, frequency response, but we're going to look at a different coordinate system. Rather than a rectangular plot like this with these coordinates, the axes are going to change. Okay, and so we'll take a look at that plot on Wednesday. Okay, right now what I'm going to do is give you back your exams. The solution has been posted on Canvas, so if you have any questions, feel free to ask questions. Class average was around 80. Okay? The solution to exam A has an error on it. So you need to go figure out what that is. If you have exam A, I think exam B, the solution is correct.